With example number 9, we see at the start of the day there's 5,000 gallons of water in a water tank. And this is a type of problem that the College Board really likes because for some reason they just use water tanks over and over again. But mostly it's because we can have water being pumped into the tank, and that's the case here, 50 gallons per hour, and water leaving the tank, and that's the case here, negative square root 5,760 minus x squared gallons per hour. We're asked to write a function, w of t, which gives the amount of water in the tank at any time for 0 to 24. So the domain itself is not all that important, other than the 0 being that's our initial value. All right, so we're going to be working off of the 0. In other words, that's going to be the low bound of our integrals. The 24 does not really come into play here. It's just an ending value for when our function is no longer valid. All right? But we want to write a function w of t, so let's start by literally writing the w of t. Okay? And we know from our previous videos that this answer should start with the initial condition. And initially, there's 5,000 gallons of water in the tank. So we're going to start with 5,000, right? And we're going to add to that all the change. Now, keep in mind, there's two changes, the amount coming in and the amount going out, right? So with the amount going into the tank and the amount going out of the tank, because they're rates, they're changes, and therefore they have to be part of our integrand. As I mentioned before, we're starting when t is equal to 0. That's when there's 5,000 gallons of water in the tank. So 0 is going to be our lower bound. Our upper bound is unknown because we want to do this for any time t. So this might be 1, this might be 20. It's anything that works between 0 and 24. As far as the integrand is concerned, well, the amount going in is 50 gallons per hour. So we have our 50. And the amount leaving, we see right there, is our negative 5,760 minus x squared gallons per hour. So the amount going in should be positive and the amount going out should be negative. We see that it is negative. Sometimes they give you a positive value here, but because water is leaving, they want to make sure that you understand that there should be a negative right there. And then we have our dt. And some of the astute-eyed observers might notice that, hey, you know what, this 50, could we, because it's just 50 gallons per hour, can we just not have that inside the integrand? And it's true, you could actually write this slightly differently. We could have this as 5,000 and then plus 50t because it's 50 gallons per hour. Well, how many hours? T hours? Boom, there we go. We just multiply that by 50. And then we just subtract our integral from 0 to t of square root, again, the negative sign is already out front, 5760 minus x squared dx. This should have been a dx right here. I apologize for that. All right. And yet somebody else may have noticed, well, can we do this in two separate integrals? And you absolutely can as well. One final way we could write this, 5,000 plus the integral from 0 to t of 50 dx minus the integral from 0 to t of square root 5,760 minus x squared dx. And this third answer would be just as correct as the previous two because they all represent the same thing. It's the change going in, that's positive, involving the 50, and the change going out, which is negative, involving that variable rate. As far as part B is concerned, write an expression for w prime of t. This ends up being rather easy. We have to derive any one of these expressions. Well, what's the derivative of 5,000? Exactly, it's nothing. What's the derivative of 50t? It's just 50. But even if you don't use this expression right here, you can use the top one. And we know that when we derive this accumulation function, all we're going to do is keep the integrand, but replace the variable that we see here with the variable that we see there. So either way, the 50 ends up in our derivative, as does the minus sign, the square root, and then 5760 minus t squared. So our derivative is right there. Notice the initial condition is not part of the derivative, but the entire integrand, all the change, is the derivative, which makes sense because derivative means change. What does w prime of t represent? Well, w of t is the amount of water in the tank at any time. Oops, sorry about that. W t is the amount of water in the tank at any time between 0 and 24. So w prime of t represents the rate in gallons per hour, because the units are important, the amount of water in the tank is changing. The derivative always represents the change. So we have the amount of water in the tank. The rate in gallons per hour, the amount of water in the tank is changing. And that will be our derivative. And last but not least is the amount of water in the tank increasing or decreasing throughout the day. Well, we know that the derivative represents change, and a positive derivative means a function is increasing, and a negative derivative means a function is decreasing. So because of the way the question is asked, we're really looking for some value between 0 and 24 to plug into our derivative. And let's find out if it's positive or negative. So pick your favorite number between 0 and 24. I'm going to pick 13, and let's put that into the calculator. So we're going to have, basically, we're looking for W prime of 13. That would be 50 minus the square root of 5760 minus 13 squared. And when we hit enter, we see that that value is negative. And in fact, if we look at the graph, which you don't have time to enter in here, but if you look at the graph from 0 to 24 of your derivative right here, you'll notice that the whole time the graph is down below the x-axis. The derivative is negative, which means our function, our amount of water, is decreasing throughout the day. All right, so decreasing because W prime of t is less than 0 for 0 less than or equal to t less than or equal to 24.